So, good afternoon, my dear students. My name is Dr. KCH Apparao, working as an associate professor in mechanical department. So, today I would like to explain about the layout of steam power plant. In previous class, we discussed some cycles which are used to generate the power in thermal power station, uh, thermal energy. So in last class already discussed the Rankine cycle and the Carnot cycle also. Today I want to give one numerical based upon the Rankine cycle. Then I will go for the layout of steam power plant. So we know that this is the Rankine cycle. So this is the basic diagram of the thermal power station or thermal power plant. So mainly it has four components. The first one is the turbine, so boiler and the condenser, the pump, heat pump. So these are the main parts of the thermal power station. We already discussed the relationship, the graph between the temperature and the entropy. So this was already discussed in previous class. So based upon this one, we already saw what was happened in this Rankine cycle according to in 3 to 4 that shows the saturated water from the condenser at state 3. Okay. So we know that isentropic means enthalpy or entropies are same. So state 4, the pump work, the pump work required. So that is represented by work done by pump and work done by turbine. So that is represented by T. We know this one. In second 4 to 1. So water at state 4 is heated at constant pressure in boiler to state 1. This one already here in the boiling, the heat will be taken, and just like condensation, heat will be leaved, just heat will be passed away. So this is the Q2, this one is the Q1, and WP, work done by the pump and work done by the turbine, and intake heat, that is the Q2 in boiling, Q1 in boiling, and Q2 the taken heat by the help of condensation. So these four parameters are very important, and these things are already discussed in last class. So based upon the Rankine cycle, so this one is the formula for the efficiency of thermal power station power plant. So efficiency of the thermal power plant is equal to W net by Q1. So W net is nothing but you know that work done by turbine minus work done by pump. So by taken heat in boiling, so that is the Q1. You know the formulas already discussed in H1 enthalpy at 0.1 to 0.2 minus enthalpy 0.4 to 0.3 by H1 minus H4. So these things already as explained in the previous class. Okay, so H1 minus H2 enthalpy at 0.1 to 0.2 minus so it is the volume into pressures P4 minus P3. So this is the formula we already discussed in this one. So based upon this formula, so we'll solve on numerical based upon Rankine cycle, how to find the efficiency of the thermal power plant, and we'll find this one by one example. So this is the example. A simple Rankine cycle works between the pressures. Two types of the pressures given here. One is at 28 bar and the 0.06 bar. So one is related to boiling conditions, another one is related to condensation condition. So the initial condition of the steam is being dry saturated. So the initial condition of the steam is dry and saturated. This is very important. Initial condition of the steam is given. So it means dryness factor, the point to dryness fraction x1 is equal to 1. So that shows enthalpy h1 is equal to hg. So based upon this one, we'll see this one. Next, we have to calculate the cycle efficiency of the cycle. We have to calculate, and the work ratio we have to calculate. Next, to specific steam consumption. So steam consumption by turbine and pump. So these things we have to find. So in this numerical, so we'll see what is the data given here, then and what you have to find the parameters based upon the data. So here some data. So the enthalpy values and entropy values should be taken from the steam table. So for this numerical, you have to use the steam table. By the help of the steam table at a particular pressure values. So we have to take those enthalpy and entropy values and the pressure values also. Okay, temperature values also you can take. So the first one, the condition, two types of pressures are given. One is the 28 bar, another one is the 0.06 bar. So these are the two conditions. You know that in thermal power plant, just there are four components, main components. One is the boiler. So another one is just like turbine. T is the turbine. Another one is just like pump. No, condenser. So condenser to pumping to boiler. So these are the main components. Otherwise you can take like this one. So these are the components. This is the condition one. So this one is the condition two. So here just like, so the first one at 28 bar. Here just like boiler pressure has been given, that is represented by PV. So boiler pressure PV is equal to 28 bar. Okay, so you know that points boiler pressure means, so this is the 4, this one is the 1, entering pressure and leaving pressure. So both are same. So P1 is equal to P4 is equal to, that is the boiler pressure PV is equal to 8 bar. So this one is the given value. Okay. Similarly, second pressure also given, that is the at 0.06 bar. So that is called a condenser pressure. We can say that is the condenser pressure. So in condenser pressure, you know that. So this one is the condenser pressure 2 and 3. So here just like in condenser pressure, enthalpy at 2 is equal to enthalpy is equal to 4, because this is the isentropic expansion. So we know that isentropic expansion means enthalpy values and entropy values does not change. So it means H F2 enthalpy is equal to at 0.22 is equal to enthalpy of uh, 0.3. So here just because this is isentropic expansion, so enthalpy is, will not change. So HF2 is equal to HF3. So first we'll see these things. First one is the at 28 bar means so the pressure which is related to boiler pressure, that is the PV. So PV means so according to the simple diagram, the boiling, entering and leaving. So 1 and 4. So P1 is equal to P4. In this condition, pressure is uniform. You know this one. So this is the 28 bar. So if you consider this is the 1 and 4, automatically P1 is equal to P4. So that is the 8 bar. So similarly, uh, condenser pressure means so 2 to 3 here. So here also pressure is equal to uniform. So pressure is same. So P2 is equal to P3. That is the 0.06 bar. Okay. So at point 1, this is the point 1. So dryness factor and dryness fraction x is equal to 1, because this is according to this condition is equal to steam is dry saturated. Dry saturated means so x is equal to 1, and h1 is equal to enthalpy at 1 is equal to hg. Hg means enthalpy of the gas, hg. So we have to note this one. So automatically then these hg values and the hf values, fluid and gas, enthalpies of fluid and enthalpies of gas. So these things will be taken, will be collected from the steam table. So according to steam table, you can refer page number 12. So in this just pressure value has been given. Based upon this pressure, we can collect the enthalpy and entropy values, and pressure values and temperature values also can collect this one. So according to page number 12, that at pressure 28 bar, so then Hg is equal to enthalpy of gas, Hg is equal to 2802, so kilojoule per kg Kelvin. So similarly, entropies S1 is equal to Sg. So S1 and H1 means enthalpy at one condition, 0.1 condition, and entropy of 0.1 condition. Those are equal to just gases, because dry saturated gas. So all the water will be converted into gas that comes into saturation position by the help of the boiler. So because of this one, then H1 is equal to Hg, that is the 2802 kilojoule per kg. So this is the value. Similarly, entropy S1 is equal to Sg. So Sg is nothing but S1. Sg values will be collected from the data table at with corresponding to 28 bar pressure. Okay. So then you can take Sg is equal to S1. The value is equal to 6.2104 kilojoule per kg. Kilojoule per kg Kelvin. So this is the value. So just to have to just remember the H1 value and S1 values. It means so enthalpy and entropy values we can collect from the data book. So in the similar way from the condenser pressure, based upon the condenser pressure, so it means at 0.0006 bar. So based upon this condenser pressure also we can collect the uh, enthalpy values and entropy values of fluid and gas, because 2 to 3 means some of the fluid and some of the liquid. Then it's just you can take the fluid values and gases values also here. So in two condition is 2 to 3, so that is the pressure. Here just like isentropic expansion, so H2 is equal to H3, and S2 is equal to S3. Entropy and enthalpy values will not be changed. So HF2 is equal to HF3. So this is 151.5 kilojoule per kg. You can take from the data book in the page number 7. You can refer this page number 7. So in the steam table book. Similarly, HFG2. So that is the value of 2415.9 kilojoule per kg. Similarly, entropy SF2 at 0.2. So SF2 is equal to 0.2521. Similarly, SFG2, that is the fluid gas, 7.809 kilojoule per kg. So VF is the volume of the fluid, that is the 0.00 meter cube per kg. Okay, these are the values we can collect from the data book with respect to 0.0 bar. This is the condenser pressure, given condenser pressure. By using this data, we can find out the parameters uh, which are given to calculate. So that is the cycle efficiency. We'll see first one. So the first condition. So 122. 122 means the boiling condition. Boiling. So this is that is the 4. The 1 to turbine. This is the condition. So one condition, 122 or one condition. So considering the turbine process. So we are considering the turbine process 1 to 2. So here just like we know that enthalpy S1 is equal to S2. S1 is equal to S2. You know that S2 is equal to, or S1 is equal to SF2 plus X2 into SFG2. SFG2. This is the formula we already discussed in previous class also. So you know that S1 value is equal to S1 is equal to SG. In last slide you can see S1 is equal to SG, that is the 6.2104. That is the, so this value is equal to SF2 plus X2. X2, it means the condition of fluid. We have to find out this one. X2 values should be calculated here. So X1 value is given. So that is the dye saturation condition. That is, this is here the condition for 4 to 1 in boiling condition. It was given. In 1 to 2, we have to consider this one. We have to find that fluid condition. So that is X2. We have to find out the X2. So this is the formula. SF2, you know this one. SF2 is equal to the given value. Here SF2 is equal to 0.2521 based upon the 0.0406 condenser pressure. Okay. So that is the value SF2 given, and the SFG2 also here given. So this one, the values are taken from the data book. So based upon the formulas, we can substitute those values. So it means S1 or S2, the S1 or S2 is equal to SF2 plus X2 into SFG2. So if you substitute these values, we can find out the X2 values. So X2 value is equal to this one is the value. If you know the X2 values, then you can find out the H2 value. Because H1, you know that enthalpy at 0.1, then enthalpy of 0.2, we have to find out. The based upon the enthalpy of 0.1 and enthalpy of 0.2, then we can find out the turbine work done by the turbine. So then the formula is equal to H2 is equal to HF2 plus X2 into HFG2. Okay. So based upon the entropy formulas, we are finding the X2 value, condition of the fluid, and so based upon the enthalpy formula, then we are finding the H2. So it means enthalpy at 0.2 at to positioning to process. So then H2 value is equal to, this is the H2 value. So then if you know that H1 and H2 values, then you can find out the work done by turbine. So this is the formula for the work done by turbine. So WT is equal to H1 minus H2. H1 is equal to, you know that already, H1 is equal to already SG. H1 is equal to HG. HG. So that 2802. So that is the value. And the H2 already we got here from this formula. That is the 1910.27. So if you subtract from H1, H2 from H1, then you will get the values. That is the W turbine is equal to 891.73 kilojoule per kg Kelvin. So this is the work done by the turbine. So finally, based upon these pressures, then we have to find out the enthalpy before entering the enthalpy of the fluid before entering the turbine, after leaving the turbine. Then H1 and H2 you have to calculate. Based upon this two, you can find out the work done. So this is the formula, work done by the turbine. Okay. So now we will see the work done by the pump. Work done by the pump. So to just to pass that fluid into boiler. Okay. So now we'll see the work done by the. Here two types of work done will be placed. One is the turbine WT and WT. So this one already calculated. Now we'll see the work done by the pump WP. We'll see how to find out the work done by pump. You know that this is the formula. Work done by pump means this one is the pump. This is a condenser. So simple diagram, you know this one. So boiler B to 1. This is the turbine to condenser C, condenser to pump P. So boiler. So this is the 1. This one is a 2. This one is a 3. This one is a 4. Okay, after condenser, this is the pump. It means 0.3 to 0.4. So H3 and H4. These two things should be known. So it means fluid of HF4 minus HF3 is the formula. Okay, so based upon this formula, you can find out this one. So this HF4 is equal to HF3. This is nothing but volume of the fluid into pressures P1 minus P2. You know that. Okay. So you know the volume based upon the steam table. According to steam table, we got this one fluid volume, and the pressures also already given in the numerical pressure at 0.1. So that is the given value, that is 28 bar, and the pressure to 0.06. These values. So if you substitute these values in this formula, you will get the work done by pump. Work done by pump. So that is the you know that VF is equal to 0.00 by 1000. So 28 bar minus 0.006 into 10 to the power of 5 bars. So conversion of units, you know this one. So if you solve this one, automatically 2.79 kilojoule per kg, you got this one. So this is the work done by pump. This is the work done by turbine. So this is the work done by turbine. This is the work done by the pump. So you know that formula. One more thing, HF4 is equal to HF3 plus 2.79. 2.79. This is the value already got here. This one. So it means if you want enthalpy of 4 fluid enthalpy at 4. So enthalpy at 0.3 plus work done by the pump 2.79. So if you add this one, you will get this HF. Then you have to remember this one. So because the network, we have to find out this one. The network net W net is equal to work done by turbine minus work done by pump. Okay, this is the useful work 891.73 minus 2.79. So this is the value. Finally, 888.94 kilojoule per kg. So this is the work done by the power plant. So this is the turbine work minus uh, pump work. So this is net work done by the thermal power plant. Now we'll see the efficiency of the cycles. Cycle efficiency, you know the formula W net by initial taken heat, so by the boiler. So Q net means W net means W turbine minus W pump. Okay, by Q1. So Q1, you know the formula of Q1, that is the enthalpy of H1 minus enthalpy of fluid 4. Okay, 4 points. So because you know that formula, that is the boiler, this is the turbines. Okay, from this one, that is the condenser to pump. So this is the values. You know that this is 1, this one is the 2, this one is the 3, this one is the 4. Okay. It means this boiling conditions means taken heat or developed heat through or heat taken by the fluid by boiler. So our conversion of liquid water into saturated steam. So the taken heat Q1. So that is equal to enthalpy H1 minus HF4. HF4 here. So differences of these two. So then Q net, it means you know that we already calculated this one. 888.294 by H1 minus HF4. So if you substitute the values HF4, we already calculated this one HF4. So in the previous slide that was calculated HF4. HF4 is equal to HF3 plus work done by the pump. So this is the value 154.29. Then you can use this one. So H1 is equal to, you know that we already know that H1 is equal to Hg. This is taken from the data. You can collect that data book, and then H1 is equal to Hg. You know that value 802 minus 154.29. If you substitute these values and simplify this one, we will get the efficiency of the cycle. That is, the efficiency is equal to 33.57%. So this is the cycle efficiency. Okay. Next, work ratio. Work ratio means Q net by W net by W turbine developed work. So work, utilized work or released work by just like work done by turbine. So you know this one. So net work done means WT minus WP by WT. This is the formula. You know the values of WT and WP and WT also. If you substitute these values, you will get these values. So W net, we already solved this one, 888.945. W turbine 891.73. So that is the work ratio is equal to 0.2997. So this is a specific steam consumption. So this is the formula. If you substitute this one, you will get this value also. So by using the Rankine cycle, we discussed how to find out the cycle efficiency and work ratio, and turbine work done with the turbine, work done with the pump. So how to collect the enthalpies and entropy values from the data book based upon the pressures. Okay, so in this way, just we can calculate we can solve the different numericals. Okay, next I want to explain about the layout of steam power plant. Layout of steam power plant. Here in this class, just I will give a small introduction about this layout. So, introduction. So, it is an important medium for producing the uh, mechanical energy. You know that steam is used to drive steam engines and steam turbines also. It can be raised quickly from the water, which is available plenty. So steam makes possibly just the steam will be raised from the water. So it does not react with does not react much with materials of equipment. What are the equipment used in the power plants? So because water does not mix it with the does not react with the equipment parts. It is stable at temperature required in power plant. So this steam is very stable at a temperature. Now we'll see. You know that already we discussed in previous also. What are the equipments of steam power plants? What are the different parts in the steam power plant? So steam power plant must have following the equipment. The first one is the furnace for the boiling purpose. A furnace for burning the fuel, different fuels already discussed in previous class also. Next, a boiler for steam generation. For the generation of the steam, we should require the boiler. For the running of boiler, we should require the furnaces. Next, we should require the turbine to convert the heat energy, what are the developed boiler, into mechanical energy. So conversion of heat energy into mechanical energy, we require the turbine. Next, we require the generator to convert this mechanical energy into electrical energy. So which is a comfortable form to transfer from one place to another place, long places also, and to store this energy also. Next, piping system. So pumping system or piping system, it is also very required to carry the steam and water from condenser to boiler. So these are the main parts required in power plants. Okay, this is the just layout of steam power plant. One of the figure. Uh, this is the boiler drum. You know this one. So for this one, fuel is required. The fuel means coal. Coal taken from the coal mines, and the coal should be prepared proper way, and should be sized by the help of some crusher, something. Next to that, the coal should be stored in a coal storages. So this coal handler, this is completely process called as coal handler. This by the help of the coal handler, the fuel is just shifted to the boiler drum, the furnace for the running of the boiler. So after um, mm, so burning of the fuel, so some type of ash will be developed. The ash handler is also very important because this is very sometimes very poisonous, and very it has lot of dust and something very heated ash also there. Handling of the ash also. Ash storage also very important. So next to steam generation of the steam for the running of uh, turbine, and just condensing of the steam for the reusability of the steam. So all these things will be given in this diagram. So we'll see one by one. One by one, I would like to explain this one. The first one, I want to. So in this class, I want to highlight this coal and coal storage or coal handling. Next, ash storage and ash handling. So these are the few points regarding the coal and ash circuit. It includes coal delivery. So coal circuit or ash circuit. So mainly it consists coal delivery, preparation of the coal, coal handling, and the boiler furnace, and ash handling and ash storage. These are the main parts just for the handling of the um, coal, fuel, and the handling of the ash byproduct of that uh, boiling. So the coal from coal mines is delivered by either ships, rail, or trucks to the power station. So from the coal mines, the coal is shifted from power station by the help of some trucks or ships or rail. The, then the coal is sized by crushers in required size. The coal is crushed or coal is sized by some crushers and breakers. The size coal is then stored in your cold storage. So that storage is nothing but a stockyard. So that is the just collecting of the coal from the coal mines. So from the stockyard, from this coal storage, the coal is transferred to the boiler furnace by means of some conveyors and some elevators. So some systems are there for transferring for the movement of the coal from uh, coal storage to boiler furnaces. Then the coal is burnt in the boiler furnace, and then ash also is formed by the burning of the coal. Right? So the ash coming out the furnace so will be very hot, too hot, and very dusty, and accompanied by some poisonous gases also. Okay. So for proper handling of the ash is very important. Proper storage of the ash also very important. So it is transferred to ash storage. Usually the ash is quenched to reduce the temperature. So quenching in some water. So to reduce this temperature and to increase the temperature of the water. So and to reduce to control the corrosion and dust also. For this process, quenching process will is used. These are the few points regarding the mainly coal handling and ash handling. So in next class, I would like to explain about the complete process of complete layout of the power plant, steam power plant. So what is the condition of steam generation, and what is the importance of the economizers and the preheaters, and what is the importance of turbines also, and next to condensations. So we'll see in next class. So I want to stop here. Thank you for listening this class. So in next class we'll continue this one. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.